Hello, everyone. Hope everyone's having a great time at AKC 2021. My name is Gamaliel. I'm a PhD candidate under the supervision of Professor Namjoon Cho in Nanyang Technological University. I'm currently at the tail end of my candidature as I've submitted my thesis and am waiting to do my oral defense. Currently, I'm working in the Singapore Food Agency in the Science and Technology Division. Today, I'd like to share with everyone here on a research topic that I did during my time in NTU, entitled Conformational Flexibility of Fatty Acid-Free Bovine Serum Albumin Proteins Enables Superior Antifouling Coatings. So protein adsorption is the spontaneous and non-specific adsorption of protein molecules to solid surfaces. Broadly, this can be broken down into three separate stages. In the first stage, the protein molecule diffuses from its liquid medium towards the solid surface, followed by the adsorption of the protein molecule. And this is then followed by a deformation or structure involving the structural rearrangement of the protein molecules on the surface, eventually leading to irreversible adsorption. Because of this structural rearrangement, the protein molecule can be said to have undergone surface-induced denaturation. So protein adsorption is a very common process and is involved in various biomedical applications, such as these that are listed here. So more often than not, protein molecules are seen as something undesirable. So for example, for immunological assays and biosensors, which rely heavily on specific interactions, such as your antigen and antibody binding, non-specific protein adsorption, for example, proteins adsorbing onto the substrate, can give rise to false positives and background noise. And this can hinder the performance of these applications. For biomedical implants and nanoparticles, non-specific protein adsorption can give rise to immune responses and medical complications such as thrombosis or complement activation. And in serious cases, this can even lead to death. So naturally, strategies have been developed to prevent non-specific protein adsorption. And one of the earliest strategies that's devised and one that is still widely used to this very day due to its simplicity is the adsorption of, or is the coating of proteins onto the surface to prevent further protein adsorption, such as how BSA or bovine serum albumin is used in Western blotting applications. So one question that we asked ourselves for this project is, can we improve the coating application, specifically surface passivation coating application, by changing the protein properties? So can we specifically increase the adsorption uptake, increase surface coverage, and thereby improve surface passivation? So in this study, we used BSA, which is, since it's one of the most widely used protein for surface passivation applications, we used that as our model protein. And we took a material science approach to try to figure out how we want to do this. So we asked ourselves, how does processing and structure of the BSA protein affect the properties in terms of the way it adsorbs, and in terms of performance, in terms of its surface passivation performance. So BSA is all well and good, but which BSA do we use? So this chart was actually taken from the Sigma Aldrich website, which shows that there are actually well over more than 40 different types of BSAs. And one would be tempted to just pick the cheapest one. But are all BSAs actually the same? So this study actually showed that BSAs obtained from the same companies or exhibited different blocking properties when used in an ELISA application. So with this background knowledge, this actually fits in very well with this study objective, which is to systematically investigate how different processing conditions can influence BSA conformational stability and adsorption behavior, and then determine which of these key processes, specifically fractionation method and fatted versus defatted BSA, which of these processes produce the most significant influence on the BSA properties, and based on this knowledge can be exploited to then improve surface passivation performance. So I'll just briefly go over the different types of processing parameters that were considered for this study. So the first would be fractionation method, which is the process of separating the BSA protein from the raw material, which is plasma. So the two most commonly used fractionation method in the industry is co-ethanol fractionation and heat shock fractionation. So BSAs that were produced from co-ethanol fractionation I've designated as BSA1. That produced from heat shock fractionation I've designated as BSA2. And one that has undergone co-ethanol followed by heat shock fractionation I've designated as BSA3. So BSAs 1, 2, and 3 can undergo a further fatty acid removal step, and that gives us BSAs 4, 5, and 6 respectively. So these 6 BSAs were used for this study, and just to note that all 6 BSAs were obtained directly from the company, and all these processing procedures were done by the company itself. So these are the fundamental characterization methods that were done to assess or characterize the properties of the BSA, 6 BSA proteins. They can be broken down into solution-based and surface-based. So for solution-based, the DLS and circular dichroism or CD method was used to characterize the molecular size and the secondary structure of the BSA proteins in solution as a function of temperature. For the surface-based techniques, I use QCMD and LSPR, which are both surface-sensitive techniques, and both of which characterize the adsorption uptake and kinetics of the BSA proteins onto silica surfaces. And ATR FTIR was done to assess the extent of surface-induced denaturation for the 6 BSAs. So moving into the results section here, I'll just briefly go through the DLS and CD results. So what we see from here is that for the DLS results, all 6 BSAs have similar molecular size from 25 to 55 degrees Celsius. So they all look kind of similar if at room temperature. But one thing would be that defatted BSAs all start to show aggregation behavior starting at 60 degrees Celsius. Whereas for the fatted BSAs, they show various onset temperatures of aggregation ranging from 65 to 75 degrees Celsius, but all generally higher than the defatted BSAs. So for the circular dichroism or CD studies, we see a similar trend in terms of how the defatted BSAs have, all the defatted BSAs have lower percentage helicity than the fatted BSAs at 65 degrees Celsius. For example, they all have less than 50% of helicity, whereas fatted BSAs all have helicities above that. So the conclusion from this is that defatted BSAs are more vulnerable to temperature-induced aggregation and conformational changes. And these differences in properties are only observable at higher temperatures. So for the surface-sensitive techniques, specifically QCMD and LSPR, we see that defatted BSAs produce greater QCMD frequency shifts, which corresponds to a greater amount of mass protein mass adsorbed onto the silica surface. For LSPR, we see greater wavelength shifts for the defatted BSAs, which corresponds to a greater amount of dry protein mass due to the greater change in refractive index on the close to the sensor surface. So overall, that would mean that this defatted BSAs have a high adsorption uptake, and that a greater amount of defatted BSA molecules will irreversibly adsorb onto the silica surface. So in order to further analyze the difference between the fatted and the defatted BSAs in terms of the conformational changes associated with adsorption, we studied or calculated the maximum initial LSPR rate, and that value shows that all the defatted BSAs will have higher LSPR initial rates than fatted BSAs. This means that defatted BSAs are stickier and have stronger protein surface interaction and likely undergo more extensive structural changes. So we confirmed this using the ATR-FTIR study, and that shows that all the defatted BSAs in generally have more extensive or undergo more extensive changes in alpha helicity upon adsorption compared to the fatted BSAs. So overall, we see that the defetted BSAs are more susceptible to surface-induced denaturation than fetted BSAs. So far we've seen that the main difference between the 6 BSAs are, even though we've looked at fractionation method and the difference between fetted and defetted BSAs, we see that the difference between the fetted and the defetted one is more significant. So in order to verify that, we did our control experiment where we compared a defetted BSA with the same defetted BSA but doped with caprylic acid. And overall, we do see the same trends in that the BSA that's been doped with the fatty acid have a higher aggregation temperature, less susceptible to secondary structural loss in solution under influence of temperature, and undergo less adsorption and less extensive surface-induced denaturation. So overall, this is the trend that we see. Defetted BSAs have poor conformational stability because in terms of undergoing more extensive structural loss in solution with temperature and more extensive structural loss upon adsorption. And we also see that defetted BSAs undergo greater adsorption uptake. So we do see a trend between the poor conformational stability and increased adsorption uptake. But how does this translate to passivation performance? So that will lead us to the next portion of our study, where we evaluated the surface passivation performance of the fetted and defetted BSAs. And so for this one, we tested how well performing the different BSAs are on flat surfaces. Specifically, in the first study, we tested how well BSAs could prevent biofouling by using fetal bovine serum, or FBS, as the biofouling agent. And we found that generally defetted BSAs are better at have higher passivation efficiency than the fetted BSAs. We did the same similar kind of comparison between the fetted and the defetted BSAs for Western blot. And so we prepared 2 different blocking solutions, one made of fetted BSA, one made of defetted BSA. And in the end, we saw that the membranes blocked by defetted BSA solutions yielded blots with more clearly resolved bands. So we also did a study testing how well these defetted BSAs perform on nanoparticle surfaces. So specifically, we tested how well these BSA coatings can prevent complement activation that's induced by silica nanoparticles. So complement activation is a pretty important thing to consider, especially for nanomedicine, as complement activation related pseudoallergy can be can result in death in serious cases. But on the whole, we did observe that nanoparticles that were coated by defetted BSAs exhibited a greater protection against complement activation. So the overall mechanistic picture that we see here is summarized in this chart, in this figure here. Generally, we see that fatty acid containing BSAs have higher conformational stability, undergo less surface-induced denaturation, and they also likely produce a lower density BSA coating. This is likely due to the presence of the fatty acids on the surface of the BSA, because fatty acids have a carboxylic group, and this confers a slightly more negative charge to fetted BSAs, and this negative charge would likely exhibit itself as or show repulsion between the different fetted BSA molecules, and this repulsion would lead to lower density BSA coating being formed on the surface. Whereas for defetted BSAs, they don't have this additional negative charge and electrostatic repulsion. So some concluding remarks from this study, that processing conditions are very important, and because as shown from this study, they do significantly affect BSA properties in terms of adsorption, adsorption behavior, and importantly, surface passivation performance. So I would like to advocate the routine reporting on the type of BSA used, because many times when BSAs are reported in papers, they do not report the type or at least the catalog number of the BSAs. So that will be important. We also see variations in properties even among the fetted BSAs, whereas the among the defected BSA, there appears to be slightly less variation. So this greater variation is likely due to different amounts of fatty acids within the fatted BSAs. And importantly, defetted BSA shows superior passivation performance. And I would like to suggest that for passivation, surface passivation applications, that one should use fatty acid-free BSAs. So I've come to the end of my presentation. I would really like to acknowledge my Professor Cho for introducing me to his group and really showing me the joy in my during my entire 4 years of my PhD candidature, and of course, especially the mentors and friends in the ETS group, and now called the TMIG group. So they've really added joy and a lot of fun in my years as a PhD candidate in this group. So I've come to the end of my presentation. Everyone, hope you enjoy the rest of AKC 2021, and hope you guys stay safe as well. Thank you very much.